Good afternoon, everybody. Today we're looking at an optimization problem where we have a running track for track and field purposes that has two straight vertical, in terms of this diagram, segments of L meters, right? And then two semicircles at either ends of the track that both have a radius of X. And so that's going to mean a radius of X meters, okay? You can measure it like that. You can measure it like that, right? However you want to look at the radius. The two semicircles are identical, okay? So its perimeter we're given as 400 meters all around, okay? So we're asked to find what values of L and X, respectively, would maximize the area of this greenly shaded rectangle inside of this track. And then namely, what is that maximum area, okay? So first and foremost, let's use the information we're given. So we're told that its perimeter is 400 meters, okay? Now, the perimeter of the vertical segments, because we're not going to look at the insides, we're not running around the rectangle on the horizontal segments. So its perimeter is going to be L plus L, so 2L, plus, now we can treat the two semicircles squished together to make one full circle. And so then we can think, well, how do we express the perimeter of a circle? We've always called that a circumference. And if you remember, the circumference of a circle is 2 pi times its radius. And so for our sake, that's going to mean 2 pi times our radius x, right? That would be our perimeter function in terms of, actually, I'm not even going to call it that. I'm just going to call it the perimeter because we have both x and L. We'll leave it as just the perimeter. But we do know the exact value of it, right? We know that this is always going to be equal to 400. And so now we have a relationship between L and X. We have that 400 is equal to 2L plus 2 pi X, okay? Now, if we're looking to maximize the area of this shaded rectangle, right, what is that area going to be? Well, the area of a rectangle is always width times length. So that'll be L times, if this is the radius of the semicircle of length X, then that means that this width of the rectangle is X times 2, right? 2 radius of those semicircles worth. And so that means that our width is equal to 2x, right? And so that means that our area would be, in very general terms, including both L and X, the area of that green rectangle would be 2x times L. Now, if we're looking to maximize this area, we can't maximize a function, at this moment at least, with two independent variables, seemingly independent. And so what we're looking to do here is find a way to relate x to L, to write L in terms of x, or vice versa, x in terms of L. And so what we can do is use this equation that we got from the information we were given about its perimeter. Let's rewrite this to have either L or x isolated, right? Have one in terms of the other, whichever one you want to use. I'm going to choose for, I suppose somewhat arbitrarily, I'm going to write L in terms of x. So I'm going to write an expression for L in terms of the variable x. And so we'll have 2L is equal to 400 minus 2 pi x, right? Getting 2L by itself, and now let's divide everything by 2. And so we get an expression for L in terms of x to be 200 minus pi x. This is very useful for us because now we have one variable written as an expression in terms of the other, and so we can plug that into our area formula that we're looking to maximize, right? And so now we can write our area as a function of only x, namely as 2x times L, right? 2x times 200 minus pi x, right? And we can multiply that through to simplify it a tiny bit. A of x is going to be 400x minus 2 pi x squared, right? And now we've done most of the hard work. We've established a function for this area function that we're trying to maximize in terms of only one variable, and we can handle that pretty well, right? How do we find the maximum value of a function? Well, we find its derivative function, set it equal to 0, find any maximum point that exists. So to do that, let's go ahead and differentiate a of x. So let's move that up here so we have enough space. A prime of x, our derivative function for the area, is going to be 400 minus 4 pi x. And so if we want to find any critical points, namely any maximums, we're going to set a prime of x equal to 0, right? We're looking for any points on the curve where the tangent line has a slope of 0, meaning its derivative function has a value of 0. And so now we're going to set up an equation here. So we're going to have 0, right? Plugging in 0 in for a prime of x, right? 0 equals 400 minus 4 pi x. And quick algebra finds us that x divided by 4 divided by pi is going to be 100 over pi. And so x is roughly, let me use a calculator here, 100 over pi. What is that going to be? What's an estimation? 30 or so? Get a better calculator? 1 second here. $31.8 or so to one decimal place, 31.8 meters. And so this is our x value. This is our only x value, right? That would find us the critical point of this function. Now we know that our area function, this is a quadratic with a negative x squared term, right? So we know what this looks like very roughly. It's going to be a frowny parabola, right? With its only critical point being a maximum at the very top. That doesn't take too heavy of an analysis to kind of come up with. Otherwise, we could do a sign diagram for the first derivative function. We could do a second derivative test to see if its concavity is downwards, meaning that we would have a maximum point at the top. Or also, if we simply take a quick look at what function we're working with, we know that this is a downwards opening parabola, meaning the critical point will be a maximum at the top. And so that means that this x value maximizes our area function. And we actually are looking for what is that area. I like that green marker for contrast. And so we should also, we're also looking for, let's answer the question. We're looking for both values of L and X that maximize the area of that shaded rectangle. And so the X value that will maximize it will be roughly 31.8. We have an expression for L in terms of X. So to find out the value of L that maximizes that area, we can plug in the value of X that we found. And so that would mean that L is equal to 200 minus pi times. Remember, we can put in 31.8 or make your life even easier. Remember, X is even more accurately 100 over pi. And you might see why that's convenient to do. Pi times 100 over pi, right? Sometimes you can save yourself a bit of work if you're mindful of the values you're using, right? These pi's are going to cancel. And so L is 200 minus 100. And so L, the length of those vertical side segments of the track, are 100 meters, right? And so that means that we are ready to compute this maximum area. We have the value of L that maximizes. We have the value of X that maximizes the area. What is that maximum area? Our max area will be, that was 2x times L, right? And so we're going to have roughly 2 times 31.8. That's not a plus, that's a times, right? 2x times L times 100. And so that maximum area leaves an approximation sign, right? 31.8, that was an estimation to 1 decimal place. So the maximum area is roughly, what is that? 63.6 times 100, 6,360 roughly square meters. And that is a rough estimation to 3 sig figs of our maximum area for this running track. So again, whenever you're given information, try to set up some equation with what you're given that lets you relate the 2 variables together, right? Usually that allows you to write an expression for one of the variables in terms of the other one, which you can then use to substitute inside of the function that you are looking to optimize, whether that's maximize or minimize. You need to find a way to relate the 2 variables that are seemingly independent at the beginning of the question. You have to find a way to relate them with some kind of information that you're given, and then use a substitution to have your optimization function be a function of only one variable, because that's the only thing we know how to maximize or minimize for now, okay? So then go ahead, find all your information, set your derivative function equal to 0, find your critical points, minimum, maximum, whatever the case may be, plug them back in and get your maximum value or your minimum value, depending on the situation. So I really hope this helps. If you guys have any other cool questions of this kind that you'd love to see solved, please post a comment below, and thanks for watching.